In section 5.7, we're going to look at the fundamental theorem of algebra. So the important thing to note here is that the degree of a polynomial equation tells you how many roots that equation has, which you might have already picked up on in the past couple sections that we've done. So for example, let's look at a quadratic equation. A quadratic has a degree of 2. And the different situations that we might encounter here are having 2 real zeros where I cross the x-axis twice, 1 real zero where I only hit the x-axis once, or no real zeros where I don't even cross the x-axis at all. And what we've learned lately is that even if I don't have any real zeros, I could have imaginary zeros. So you're going to see with the combination of all these how I get 2 roots every single time. So for example, if I had an equation like x squared minus 4, if I factor that out, I get x plus 2 and x minus 2. So I have 2 real roots at x is negative 2 and x is positive 2. There I have 2 real roots. If I had a situation like x squared minus 2x plus 1, if I factor that, I get x minus 1 twice, or x minus 1 squared. So I have a root at 1 that has a multiplicity of 2. There, in a kind of a roundabout way, still giving me 2 roots. And then finally, if I had a situation like x squared plus 2x plus 2, I can't factor that, so I'd use the quadratic formula. And when I do all that, I end up getting 2 complex roots, or 2 imaginary roots. So here I have, again, 2 roots here at negative 1 plus I, negative 1 minus I. But notice here in all of these different situations, I get 2 roots every time. So that essentially is what the fundamental theorem of algebra is. The fundamental theorem of algebra states that if p of x is a polynomial of degree n is greater than or equal to 1, then p of x equaling 0 has exactly n roots, including multiple and complex roots. So let's end this by doing a couple examples here. So these can be kind of long, so make sure that your notes are organized here and you have every step written out. Here I want to find all of the roots of x to the 5th power minus x to the 4th minus 3x cubed plus 3x squared minus 4x plus 4 equals 0. So right out the gate here, I'm going to see if I have any rational roots or real roots. And I do that easily by graphing. So when I graph this equation, here's a rough sketch of it. I see that I cross the x-axis at negative 2, 1, and 2. So my roots so far, I know I have roots at negative 2, 1, and 2. But notice here, my degree is 5. So there's 2 more roots that I can't see, meaning that they have to be imaginary. And how I'm going to find these is I'm going to use those rational roots, break down this equation a little bit, and then solve for x. So step 2 here is I'm going to divide out all of the rational factors using synthetic division just a repeated number of times. So here I'll start by using negative 2. I'm going to write out all my coefficients, and that's how I'm going to start out my synthetic division process. So I'm going to bring down that 1. 1 times negative 2 will give me negative 2. I add those factors together, I get negative 3. Do the same process again, I get 6. Add together. Same process again. Add. Again, just keep repeating that process. Finally, since negative 2 is a factor of this equation, I'm going to get 0 at the end here. And now I repeat that process again. I'm going to go with 1 now. Do the same process. And when I divide everything out, again, I should get 0 because, again, 1 is also a factor. And then I do the same process again. Bring down the 1. Factor out. And I'm left with the equation x squared plus 0x plus 1 equals 0. Or, for short, x squared plus 1 equals 0. Now I can solve for x. So all I'm going to do here is I'm going to bring that 1 over. Take the square root. Know that the square root of negative 1 is I. And my answers here could be positive I or negative I. And again, that kind of leads into that rational root theorem where conjugate pairs match up. So my last 2 factors here are positive I and negative I. And those are all of the roots, all 5 of them, to that equation. Let's do one more example and call it a day. Here I want to find all the roots of x to the 4th power plus x cubed minus 7x squared minus 9x minus 18 equals 0. So here, since I have x to the 4th power, I know I'm going to have 4 roots. Again, I'm going to start here by graphing this equation, seeing if I have any rational roots to start here. Here when I graph it, I get something that looks like this, and I have roots at negative 3 and positive 3. And I'm going to use these in step 2 as I synthetically divide. So I'll start with negative 3. Also, just before I get started here, it doesn't matter what order you start with. I could start out by dividing by 3 and then doing negative 3. All of those numbers are factors of this equation, so the order here doesn't necessarily matter. But again, moving forward, I'm going to bring down that 1, synthetically divide everything. Just a good rule of thumb to know that you're synthetically dividing correctly is that you should get 0 as your last number every time, because again, I'm not going to get any remainders here because I'm just dividing out factors. Now I'll use synthetic division for that other root, 3. Bring down the 1, do the same process again. And I'm left with the equation x squared plus x plus 2 equals 0. And now finally, to find my last 2 roots, I'm going to solve for x. So bringing that equation over, here I'm kind of stuck here at a factor, so I'm going to have to use the quadratic formula. When I plug that in, I get something like this. Simplifying under the radical or the discriminant, I get negative 7. And then to kind of simplify that, I can pull out that negative 1. So I'm left with negative 1 plus or minus I square root of 7 over 2. Notice how these are conjugate pairs, so they're both going to be roots. My last 2 roots is negative 1 minus I square root of 7 over 2 and negative 1 plus I square root of 7 over 2. And finally, I'm done.